All right, so in this video, I'm going to talk about states of matter, okay, and heating currents and how they relate to one another. But most importantly, energy and how energy relates to states of matter. Okay, so here we have, for our purposes, we'll talk about the three basic states of matter. We have solids, liquids, and then we have gases. All right, and so if we were to zoom in and try to figure out why molecules or substances are in that particular um, state of matter, we have it that, okay, so like for example, in the solid state, all right, we have these intermolecular forces that are bonding these elements together, or these compounds or substances together. All right. And because these intermolecular forces are strong, it keeps everything nice and rigid. So the only type of movement that you have between each of these molecules, all right, is just some vibrational movements. But because the bonds, the intermolecular bonds are really strong, they can't go anywhere. Okay. And so if you were to give this substance energy, all right, so we're giving it energy. All right, so this all in all becomes an endothermic process. If you give it enough energy, what begins to happen is that then you're giving the molecules more kinetic energy. The more kinetic energy it has, the more it can move. The more it can move, then what it will begin to do is it will begin to start um, it will actually have enough energy to start overcoming some of these intermolecular forces. All right, and so as it's overcoming the intermolecular forces, well, at least not totally, but mostly as it becomes as it overcomes it, all right, then what's going to happen is that then the compound, all right, will go through a phase change. All right, and so this phase change is what we call, at least from solids to liquid, we call this melting. Okay, all right, so this phase change that's going to take place is going to allow the molecules to move a lot more freely. All right, there are still some intermolecular force, but it's not as strong. All right, because the molecules have more kinetic energy. All right, so this is the reason why you see liquids tend to flow, or molecules of a liquid tend to flow around each other because there's more kinetic energy here. And then once again, if you decide that, okay, you're going to add more energy. So let's add more energy. More energy. This time we need a little bit more energy this time around. All right, so that overall, this is an endothermic process. Then what's going to happen once you're going to overcome, or you're going to give the molecules enough energy to completely overcome the intermolecular forces that binds them together. And when you do that, that allows the molecules to move completely freely wherever direction they want to go. All right. This will cause another phase change. Now, in this phase change, we simply call it boiling, or we call it evaporation. In this case, now we're going from the liquid state to the gas state. Now, at the gas state, all right, what happens now is that these molecules are free to move around. There's tons and tons of kinetic energy, okay? And so now there's tons and tons of kinetic energy. They're moving freely, and so on and so forth. So now we have a substance at gas stage. Now, of course, there's other phase changes. You give gas a lot more kinetic energy, you give it more energy, then you'll go into a phase change where we call ionization, and ionization will allow the substance to become a plasma. Okay. Now, the vice versa could also take place. So let's say in this case here, um, so let's say, whoa, that you begin to take this gas, all right, and you begin to start stripping energy. You're taking kinetic energy away from it, all right? So all in all, this process is going to be whoa, this is fat. Let's skinny this down a little bit. Overall, this process is going to be an um, at X. Oh wow, did not get it small enough. Apologize. Whoa, got the eraser small. I just don't have my letter small. All right. Anyways, what I'm trying to say is that there you go. Now overall, this is an exothermic process. All right, because energy is leaving it, and once you can get enough energy out of it, what you're going to do is that you're going to start to reestablish the intermolecular forces. All right. And so, as you're reestablishing these intermolecular forces, then you're going to go through hence a phase change. All right. And so this phase change that we're going to have here, all right, so let me just kind of erase this a little bit. This phase change, all right, going from here to here, all right, we simply call this phase change condensation. Okay. Now, condensation will lead us back to our liquid state. All right, so once again, let me just kind of erase all this. It will take us back to our liquid state. Now, we're in our liquid state. Let's say you decide that you're going to take energy away from it. All right, just like we did the last time. So if we're taking energy away, all right, once again, this is an exothermic process. So much like you put water into a cup of water into a freezer, whatever the case may be. So when this happens, you have an exothermic process that takes place. All right, then once again, you're going to strengthen the intermolecular forces because the molecules don't have as much kinetic energy anymore. And so as they don't have as much kinetic energy, these intermolecular forces are getting stronger and stronger. Now, it will cause that the molecules cannot move as freely as they want to anymore. And then when this process happens, once again, you have another phase change. All right, and so this phase change, all right, is the phase change that we call freezing, or let's give it a really big term. We call this solidification. Whoa. So solidification. All right. And then when that happens, once again, you have reestablished these intermolecular forces that are keeping the molecules still. All right. And so these intermolecular forces allows the molecules to become what we call the solid state. All right. So it's always this moving around of energy. So as you put energy into the system, then the higher energetic the physical substance may be. So you give energy to solid, you eventually get to his liquid form. You give energy to a liquid, then eventually it's going to get to his gaseous form. And then if you take energy away, it will go completely backwards. All right. And so at the end, you'll have something like this. And so this is the reason why um, when you're looking at this, that's why least amount of energy. Oops. Um, So the least amount of energy, all right, is here. So least amount of energy, you're most likely gonna have in a solid state. Most amount of energy, a lot of kinetic energy, then you're gonna have some substance in this gaseous state. And then the in between, you're gonna have that substance in its liquid state. This diagram here is what we call a heating curve, all right? And so I'm going to show you exactly how the heating curve is related to the states of matter, what I was showing you just a little bit earlier. All right, and so if you look at the diagram at the top, all right, here it's another version of the diagrams I was showing you earlier, the particular models of this substance. So this substance in particular is water. So here in this portion here, water is your solid. All right, and then you could tell that here, we notice they're rowed, they're in a nice column, they're organized well, strong intermolecular forces. Okay. This section here, you see that we're in the middle of a phase change. All right, so we got during the phase changes, you have two phases going on at the same time. All right, and so like for example, when you're holding ice and you're holding ice long enough that it begins to melt, you're experiencing water in two different phases. All right, you're experiencing it in its both in the solid form. So here's the solid form, and you're also seeing it in its liquid form, which is here. All right, so you have two phases of water at the same time. All right, and so this point is when we're melting. All right, and then when it completely melts, all right, we have our liquid state. Okay. Now, once you boil liquid long enough, all right, then you have it where it's evaporating. And so this is something that you guys should have all seen, like especially if you're cooking something. So you put on a pot, add some water, you need to boil the water, you turn it up. You want the water to be hot enough. But what you're noticing and you're experiencing is that water is at two different states of matter. All right. And so not only that you have the liquid water that's really, really hot, but then you also see water vapor or steam come up. So here is your gas, all right, and this is your liquid, all right. So you're experiencing water in two different phases. Now, once the liquid's completely gone, then we have the gas phase altogether. Now, how does that relate to this graph here? Okay, well, this graph is basically heat versus temperature. So he added over usually some amount of time versus the temperature. Now, if you notice this segment here, okay, so we're gonna go through segment by segment. This segment here is illustrating the solid state. All right, and so anytime you have water, so let's say we started with ice at negative 40 degrees, we add energy to it. All right, the temperature will begin to increase. Okay. So it increases up until it hits about 0 degrees Celsius. Now, if you know anything about water, at 0 degrees Celsius is when water begins to melt or when ice begins to melt. Now, the interesting thing about anytime a substance is going through a phase change, the energy that you're adding to this, all right, will not increase the temperature. All right. The energy is actually being used to break down, all right, or yeah, basically to break down the intermolecular forces that's keeping the molecules together. So now instead of being in a liquid form, or solid form, now it's changing to the liquid form. So the energy that's is being added is changing or releasing itself from that intermolecular force. So now that once you add enough energy and you've done it to all the molecules, and when all the molecules are following in this liquid form, then what's going to happen? Then you'll start to see the temperature rise again. And when the temperature rise again here, now you know the water, it is at its liquid form. Okay? And this will remain up until it hits about 100 degrees Celsius. Now, at 100 degrees Celsius, water has reached another phase change. Now this phase change, all right, it is boiling, all right, it is evaporating. So the energy that's being used, okay, so the energy that's being used to heat up the substance, all right, that energy is being used once again to break up the intermolecular forces. All right. So the temperature will not increase. If you notice, there's no increase of temperature here. All right, because the energy is being used to break up to get the water from its liquid state to its gaseous state. And you can actually kind of test this out at home. So, like if you just say you take the pot of water again, you take a thermometer that can handle that type of temperature. All right, and you begin to boiling, you'll notice that at cold water, whatever the case is, it will start somewhere down here and it will increase. It will increase until you start to notice it boils. And once it boils, it doesn't matter. As long as you got liquid water, that temperature will not increase. But you will notice that you have lots of gas coming up, lots of steam coming up, all right? And this will be so up until you finally get all the water to boil and become its gaseous state. And once you could, if you could capture the steam and you could sufficiently heat it up some more, then what you'll know is then you'll see an increase of temperature as it's in its gaseous state. Okay, so just to kind of retract a little bit, and I know there's a lot of things going on here, but originally, you got it in the solid form. All right, solid form, very rigid. All right, you heat it up, the temperature will increase. All right. Then you have at its liquid state, when you start to boil it, I mean melt it. All right. So melting, you will have it both in its solid liquid state. We also call this phase change fusion. All right. This is going to be important. All right. So fusion is just the phase change between the solid and the liquid. All right. And once you get it to enough its liquid form, all right. And so here we got some movement now. All right, and so that's the liquid form. You could heat it up, the temperature will change in that state of matter. All right, and then when you finally get it to the boiling point, the temperature remained the same. Energy is now being used to get it from its liquid state to its gas state. All right. And then once that phase change completed, then you have gases, and the gases are completely stripped away from its intermolecular forces between each other, and they're free to move around accordingly. All right. So just to kind of backtrack a little bit, um, this phase change here, all right, we call it vaporization. All right. So as I said, this is really an important term that you're gonna need to know. All right. So the phase change between liquid and solid, we call it fusion. Phase change between um, gases and liquids, we call it vaporization. All right. Now, if you notice, if you're going this way, all right, this process is an endothermic process, all right, because it needs energy in order for it to go from solid to gas, all right. And the opposite is also true. If you go this way, this is an exothermic process, all right. You need to take away energy. So if you notice, if you start here, right, at the gas state, to get to solid, it will have to lose temperature. It will have to lose kinetic energy. And in order for it to lose kinetic energy, it has to release it. And the phase changes, once again, will be the same thing. As it's going through the phases, the temperature itself will change. The amount of kinetic energy it has will not change until either the intermolecular forces are restored. If you're talking about exothermic, or if you're going the endothermic route, intermolecular forces are broken up. All right, and so these are that's kind of the basis of reading a heating curve. All right, so here is just a more simplified heating curve. All right, so that way you kind of really see what's going on. But just to really illustrate some important points about the heating curve that I want to make sure that you guys understand. All right, so the first part, once again, here at this segment here, we have your solid. All right. So anytime you have a slope, it's a certain state of matter. Okay. So this slope that switches always on the bottom. All right. Regardless if it's a heating curve or cooling curve is just this backwards. All right. The slope that you find here on the bottom is always your solid. All right. Now, what you find in between, in this case, well, I'm gonna do this in blue. This case, right, is B. All right, as you're going this direction, you are melting. All right, and we also call this the change of enthalpy. And what type of change of enthalpy? We call this fusion. Okay. So anytime you have a straight line or a plateau, this represents a phase change. All right. Now, this phase change always takes place because the heat that's being added, energy is being added, is just used to either break or restore the intermolecular force. All right. And so in this section here, in B, you have both a mixture of solid and liquid. All right. And if we're going towards the right, if we're going this direction, all right, more liquid is being produced, less solid, the solid's turning to liquid, all right, until you finally get to a slope. All right, now this slope here, you have a liquid phase. So the slope that's dead in the center of the phase change or of the heating curve is always your liquid, all right. Um, and here you always have an increase of temperature, all right? In any state of matter, you will have an increase of temperature. And then after that, then you will finally reach another plateau. This is another phase change, all right? Now, this phase change in particularly, if you're going from C to D or going C, whatever, um, here we have this is boiling, or sometimes we call this the enthalpy change of vaporization. All right. So this phase change will occur up until all the liquid has then become a gas. Now you could calculate the heat of each segment of the heating curve. All right, so depending on where it is, all right, on this graph here, depends on basically what equation that you're going to use. So anytime you have a slope, all right, like what you see here, here's your solid, your liquid, and your gas phase, you will use Q equals m times C times delta T. All right, Q equals m times C times delta T, Q equals m times C times delta T. Anytime you're dealing with a slope, remember that's when you're in a particular phase or a particular state of matter. All right, if you're looking at a phase change, all right, then basically what's going to go on is that you're going to use the heat of. So here you use the heat of fusion multiplied by, here they said the mass. Sometimes the heat of fusion is also given to you in kilojoules per mole. So then you'll use the moles, all right? Same thing here. All right. In this case, you use the heat of vaporization of that substance. So how much energy will it take for it to vaporize, in this case, to get it from either liquid to gas or gas to liquid? Here, heat of fusion is how much energy it takes for it to go from solid to liquid or liquid to solid. Same idea. All right. And then the M is your mass. So heat of vaporization is given to kilojoules per grams. Then you multiply by the mass. If it's given to you in kilojoules per mole, then you multiply by the moles. All right, it really just kind of depends. All right, and Q, once again, is just energy. So depending on where it is on the graph depends on which equation that you use. All right, now also, let's just say if the temperature differences goes between different stages, all right, then what you're going to have to do is calculate each of these Q's separately, and then you're going to have to figure out the total. So the total amount of heat absorbed is the sum of all five equations. So like for example, if I tell you, okay, let's start from a temperature that's way below zero to temperature that's way above 100, if that's your temperature difference, then you're going to have to calculate each segment separately. And then once you calculate each segment separately, then you add all the Q's together, which will give you the Q total. Then what tells you how much energy it took you from the initial temperature all the way to the final temperature. Hopefully that makes sense. If not, let's just go through a couple examples so you know exactly what I'm talking about. All right, so here's an example problem. Okay, so how much energy to heat 15.0 grams of H2O from 15 degrees Celsius to 120 degrees Celsius? All right, so the first thing you need to do when given to your problem like this, when you're trying to figure out how much energy and you got a heating curve, you need to actually plot it on a heating curve so you know exactly what you need to do. Because as I said, depending on your temperature range depends on how many steps this is going to take. All right, and so we're just going to kind of zoom in here. All right, so it says from negative 15 to positive 120. All right, and so if you pay attention to this, so we're starting at negative 15. So negative 15 is roughly here. All right, so here I have segment one. So this is my first segment. So that's going to be my Q1. All right. Then after that, then you go from here. So then it has to melt. So that's my Q2. That's my second segment. Then once it melts, okay, then it goes through. Remember, we're going to, if you recall, we're going to 120. We start at negative 15 to 120. All right, and so then it has to become a liquid. So it must go through its liquid phase. So this is Q3. So we have three different calculations so far. Then the liquid must boil. So we need to take an account of the energy it takes for it to boil. So that's Q4. All right. And so that's the fourth one. Then after it boils, then you heat it up as a gas, and that's Q5. So in this case, we're going to do five different calculations. So remember, as I said, anytime you're given a problem like this, the very first thing that you need to do is sit back and look, okay, what am I doing? All right, what part of the graph I'm looking at? All right, because for An example, I could have started out um, at -15 and end at 50. All right, and so that means then you're only going to do three different calculations: Q1, Q2, Q3. Or I could start at 50 and go to 120. So then all you're really looking at is liquid when it boils and the gas state. So you really just have to kind of pay attention to the problem itself. Whoa, trying to erase this. You're really going to have to pay attention to the problem itself so that you know exactly what you need to do. All right, so as I said, in this problem, we already know we have five different calculations that we have to do. All right, and so let's go ahead and, whoa, oh, here it is. And so let's go ahead and let's do this. All right, so let's start calculating Q1. All right, so Q1, the equation that we use is m times c times delta t. All right, so I'm going to do this in purple. Q is m times c times delta t. M is your mass. What is the mass? 15 grams. So it's 15 times, what is c? Well, c in this portion, this bottom portion here, we had a solid state. So sometimes specific heat of a substance is different depending on what state it is in. And so for ice, since solid water is ice, the specific heat for ice is 2.01. All right, so I'm gonna multiply that by 2.01, or 2.09, I'm sorry. And then I'm gonna multiply by the delta T. Well, what is delta T? Well, let's look at the graph to find delta T. We see that our initial temperature or our final temperature here of this first segment is really 0 degrees. All right. All right. So that's your final temperature, and initial temperature is -15. So it is 0 minus -15. That's what's going to give us Q. Okay. And so when you plug this into the calculator, you should get for Q1 15 times 2.09 times, really that's a positive 15. All right, and so here we got about 470.25 joules of energy. All right, now let's go ahead and calculate Q2. So Q2 is delta H fusion equals times M. And as I said, mass, it just depends. M could be moles, M could be mass. It depends on what you have. So here I gave you what's the delta H of fusion. I said the delta H of fusion is 6.02 times 10, 10 to kilojoules per mole. Since the unit here is per mole, then we're going to have to change this number of this 15.00 grams into moles. All right, and that's what we have to do. All right, and so it is, in this case, it's going to be moles times the delta H. So your delta H here, so I'm just going to kind of rewrite it. Um, delta H times your moles. All right, so delta H is basically 6.02 kilojoules per 1 mole, right? And so just kind of using some stoichiometry just to help me out with this one. What I do know is um, that we have 15 grams of water. All right, and the molar mass, so for every 1 mole of H2O, it's roughly about 18 grams. And I'm just going to keep it simple as that. So that way grams could cancel out, grams of H2O could cancel out, moles of H2O could cancel out, and then all you're left with kilojoules, which is that's kind of what we want here. All right, and so you plug this in the calculator, 6.02 times 15 times, or actually divided by 18, and then we get 5.02 kilojoules because that's what we have. So kilojoules, cool, great. All right, now let's look at the third segment. The third segment is here. All right, so Q3. So Q3, we're using M times C times delta T. So our mass, again, is 15 grams times C, but this is C of a liquid water. So we look at water here, and this is the liquid, so it's 4.18. all right, times the temperature difference. So look at the graph. What's the temperature difference? This is your final, this is your initial. And so here, the final, if you look back, this is at 100 degrees. All right, this is at 0 degrees. So it's 100 minus 0, which is really just 100. All right, and then you plug this into the calculator. So 15 times 4.15 times 100, and you get 6,225 joules. Okay, so that's Q3. Now Q4, if you notice, is that you're boiling now. So you use the heat of vaporization. So delta H of vaporization times the moles. All right, so same idea what I did last time, but the heat of vaporization is 40.8 kilojoules per mole. So 40.8 kilojoules per mole. All right, I'm starting out with 15 grams of H2O. I need to change this grams to moles. So I know that for every 1 mole of H2O, it's roughly 18 grams of H2O. That's just using the molar mass from the periodic table. All right, so I cross out grams, I could cross out moles. So I'm left with kilojoules. So when I plug this into the calculator, I'm going to get 34 kilojoules. All right. And then last but not least, we have Q5. Now Q5 will use mass times C times delta T. All right. And so just to kind of give you guys a little bit more room, just going to scoot this up a little bit. All right. Actually, we'll need this part here. Okay. So Q5. All right, so the mass is still 15. Specific heat of steam is 2.01. All right, multiply that the temperature difference. So now we ended at 100 degrees and we're going to 120. So then the temperature difference really is 120 minus 100, 120 being the final, 100 being initial. So really that's just 20. So when you multiply 15 times 2.01 times 20, we get 603 joules. Now, what we're going to have to do is add them all up so that we can figure out how much energy it really took to go from negative 15 degrees to 120 degrees. All right, and so here are our Q's for each one. Now, the one thing that hopefully you will realize is that these units, not all of them are the same. All right, and you're gonna have to make them the same. Okay, so for this sake, because I know I never stated this in this question, which unit I wanted in, it could be either joules or kilojoules. I would just suggest that you just really pay attention to the question so you know which way you want to go. All right, but in this case, I want to just change everything to kilojoules. So whatever is not joules, I change to kilojoules. All right. So in this case, I have three things I need to change to kilojoules. So the first one, and to change it to kilojoules, from joules to kilojoules, you move the decimal 3 times to the left. So Q total, all right, in this case, is this Q1 plus Q2 plus Q3 plus Q4 plus Q5, because since we did 5 different calculations. So Q1 is 0.470 0.25 kilojoules plus Q2, which is here, is 5.02 kilojoules plus Q3, which is here, is 6.225 kilojoules. All right. Q4, which is here, is plus 34 kilojoules. And then lastly, Q5 is here, which is just 0.603 kilojoules. So when you add them up together, you'll get 0.47025 plus 5.02 plus 6.22 plus 34 plus 0.603. When you add them up together, you find that it took 46.3 kilojoules for you to go from negative 15 degrees Celsius to 120 degrees Celsius. All right. And that's how you'll do a problem like this. I would highly suggest that you just review it as many times until you really understand what's going on and how you do the math. All right.